Section 7.2 deals with the volume of a solid of revolution. And so now that we can find the area between two curves, imagine that we take one of the areas in question and rotate it about an axis of our choice, forming a three-dimensional solid. So for example, if we had a parabola, a parabolic area over here, say maybe this area, and that was the area we were looking for. Imagine taking that and spinning it. What type of shape would it make? If I spun it around the x-axis, what would it make? It would make, imagine it comes all the way around. So it would make like a thick frisbee type thing, right? Like a disc. Yes, like a discus maybe that we throw in track, something like that. Do you guys understand that? Okay. So what we want to do is we want to imagine taking a specified area beneath a curve, and then we're going to spin it around a designated axis. And depending which way we spin it, we'll decide what shape it makes. So we're going to learn today to calculate the volume of that shape. As long as the area we are revolving is flush with the axis of revolution, we can use something called the disk method to calculate the volume in question. The disk method gets its name because it actually calculates infinitely many volumes of circular disks that together add up to the entire volume of the shape in question. So basically I can take any shape that is round on at least one side, and I could slice it into a bunch of disks, and I can calculate the volume of those disks, and I can add it up, and that will give me the volume of the whole shape. So to find the area, what you do is you find like the area of the top of one of those disks, and then you multiply it by the height. So really you're adding up the volumes of a bunch of cylinders, because you take the area of the circle and then you multiply it by the height of that disc, and that calculates the volume of each disc, which turns out to be just a tiny cylinder. So imagine taking a rectangle and spinning it around an axis. The shape forms a disc much like a tomato slice or a slice of a tree ring. Geometrically speaking, the volume of a disc can be found with the formula V equals, and this is going to be the important one, pi times r squared w, where r is the height of the rectangle, also known as the radius of the disc, and w is the width or thickness of the disc. And then applying a definite integral to this formula tallies up the volume of all the discs that make up the graph in question. I know that sounds really abstract, but once you see it a couple of times, it's not too bad. So the formulas we're going to use to set up our definite integrals are as follows. So this is what we call the disk method. If you have a horizontal axis of revolution, such as the x-axis or another line, such as y equals 2, y equals 3, y equals 5, something like that, if the axis of revolution is horizontal, the volume is always going to equal pi times the integral from a to b of r of x squared, and that's going to act as your radius squared. You might also see that as like the height of your rectangle sometimes. This will be your primary equation usually with respect to x. So if we go back to that pi r squared w, this is your pi, this is your r squared, the radius, and this is the width, the dx axis, the width of each of your individual rectangles. And then the limits from a to b sort of depend on where you're starting and stopping. You'll either be able to figure that out on your own, or it will be given to you. If you're revolving around a vertical axis, so if you have a vertical axis of revolution, the only difference is that we'll have a dy here, and that our primary equations will be with respect to y. It'll still be pi r squared dy, but this time it'll be integrated with limits of integration that are y values rather than x values. So just sort of like when we were doing area, this is your left, and that's your, this is your, I can't think it through, you guys.
The top and the bottom?
No, the top and bottom goes here. This would be left, right, because your x-axis, like this would be A, B, and so it would be trapped somewhere along the x-axis. And then over here, the C's and D's would be trapped somewhere like here. Those are going to be y values if you're dy, and x values if you're dx, where capital R is the axis minus graph equation. So this is kind of important as well. Capital R is the axis of revolution, minus the graph equation, or the graph equation minus the axis, whichever is positive. I know that sounds a little strange right now, but that'll come in handy later. So capital R is calculated as the axis of revolution minus the graph equation, or the graph equation minus the axis of revolution, whichever one is positive. And it really doesn't matter because when you square it, the negatives would go away anyhow. So make sure you jot all that down, and then we'll start looking at some examples. So for this first example, we want to find the volume of the solid formed by revolving the region bounded by the graph of y equals the square root of sine x and the x-axis about the x-axis, where x is between 0 and pi. So if we use our graphing calculators and we kind of type in y equals the square root of sine x and we zoom trig it, each one of these dots here, tick marks, is pi over 2. So what we have is this is 0, this is pi over 2, this is pi. So just so we can kind of see it. And it ends up looking sort of like a semicircle. It ends up being a perfect kind of little semicircle like this. Now there's another piece over here, because all trig functions are periodic and they repeat, but it's told us only to worry about the piece between 0 and pi. So here's one of our boundaries, and that is y equals the square root of sine x. And then it also tells us to trap it along the x-axis. So far, so good? Mm-hmm. And then it tells us to revolve it around what axis? The x-axis. Okay. So what we have here is a horizontal axis of revolution. And it's going to help you guys if you do this. If you draw what we call a representative triangle. So you can draw it anywhere in there. So I want to take this area and I'm going to spin it this way. And imagine that, did I say triangle? I meant rectangle. Okay. A representative rectangle in here. And so this is my upper bound graph and my lower bound graph right here. The height of this rectangle right there, that's going to be capital R. That's how you'll calculate capital R. Now you'll have to look, and they told us this time just to go from 0 to pi. So this is going to be your A, this is going to be your B, the width of this rectangle is your dx, and the height of this rectangle is your capital R. So we're going to plug into the formula, capital V equals pi integral from A to B of R of x quantity squared with respect to x, because we are doing a horizontal axis of revolution. Now imagine if you spun that, what shape would it make? You imagine spinning this entire shape that I've outlined in blue.
Like the inner tube thing.
Is it a sphere or is it an inner tube?
It looks like more of an elliptical,
It's kind of
So sort of a football shape, sort of like that. Because there's no space between what we have trapped here and what we're rotating around, it's going to actually form a solid. Some of these are going to end up forming something like we talked about earlier, where you will have like a hollow place in the middle. This one won't, because we say it is flush with its axis of revolution. If I were going to revolve it around y equals -1, it wouldn't be flush.
Right.
So you kind of have to be a little careful there. And then it would definitely be that weird inner tube shape that you're talking about. But this one's going to end up just being sort of like a sphere or a football. Okay, so we have V equals pi times the integral from A to B, and they told us to go from 0 to pi of R of x. And R of x is equal to this trapped area right here, which that's just square root of sine x, right? Mm-hmm. Minus the axis of revolution, which is -0, right? The axis of revolution is the x-axis, that's y equals 0. So this one's just 0, right guys? Okay, so that cleans up to square root of sine x. And then I have to substitute it in and square it. So the square root of sine x quantity squared with respect to x. And then you clean up this, you need to go ahead and probably square it out. It's going to make your integration much easier. So we have pi times the definite integral from 0 to pi of just plain sine x with respect to x. And then we integrate that, and it integrates up to negative cosine. So we have pi times the integral of negative cosine of x from 0 to pi. And finally, if we substitute pi in, we have this pi right here already, all multiplied by the negative cosine of pi minus the negative cosine of 0. Right, guys? Is that correct? Tell me I plug that in right?
Yes.
Okay. So what is the cosine of pi?
1.
Negative 1? So a negative negative 1 becomes a positive 1. So really we have pi times positive 1 minus a negative makes plus the cosine of 0, which is also positive 1. And that gives me a final volume of 2 pi. And just like areas of circles have pi's in them, your volumes of your solids of revolution, because we're spinning them in a circular manner and rotating them around an axis, they're going to have pi's in them. So it's really pretty simple if you can get a decent graph without a lot of trouble.